Hello my learners, and welcome to a video tutorial where we are going to talk about current and resistance. So, current is any motion of charge from one point in space to another. And so let's imagine that I've got a wire here, and I'm going to put just an imaginary cylinder like this. And I'm going to give this thing a cross-sectional area A. And let's say that I've got some charges here. And all of these charges move with what's called a drift velocity, which is generally written as Vd. Now, the distance that they travel through my imaginary cylinder here, if they're all traveling at a constant drift velocity, then this distance is just going to be Vd, and this imaginary cylinder, we'll say it takes a time dt to travel across that distance. Now, the definition of current, which is denoted with an I, is dq over dt. Let's go ahead and fit that in. There we go. Now, dq over dt. Well, what's dq? dq is how much charge flows through my imaginary cylinder here. So, to get dq, here's what we're going to do. We're going to say that all of these charges have a charge, I'll just write it as little q. And how many charges are there? Well, we'll say there are n amount of charges. Now, how many flow through here? Well, in order to get that, I need the volume of this cylinder. Well, the volume is going to be its area times its distance. Well, its distance is Vd dt. My drift velocity times dt. So, there's dq and there's dt. So to get current, I equals dq over dt. So what I'm going to do is divide both sides by dt. I equals dq over dt, which equals the charge that I'm dealing with times how many charges there are times the area times Vd, because I divided dt to both sides. So this is the general definition of current. Now, something that's useful when we're talking about resistance is current density. Now, current density is denoted with a J. And current density is basically how much current over a given area. Now, we've written current previously as dq over dt, which was N times our charge times A times Vd. Well, if I take current and I divide it by area, well then this A cancels, leaving me with just a current density Qn times Vd. Current density is measured in amps per square meter. The unit on current is amps. And 1 amp is 1 coulomb per second. Okay, so let's talk about resistivity. Resistivity. Okay, resistivity for most metals, most conductors, at a given temperature, J, our current density, is directly proportional to the electric field. And the electric field is what's causing that drift velocity. Now, a material's resistivity denoted with rho again, is denoted as the electric field over J. And for most materials, for most metals, as long as your temperature doesn't get too crazy, high or low, then this proportionality here is a constant. And this right here is Ohm's law. Now again, I use law loosely. This works for some materials some of the time. So we'll obviously use it for those materials at those times. Now I said at a constant temperature. If you take a metal and you up its temperature, well, you're also going to up its resistance. Here's why. Whenever you increase a metal's temperature, you're giving energy to all of the electrons, but you're also giving energy to the ions inside that metal. And you're increasing the likelihood that the electron is going to bombard with an ion, therefore effectively slowing down its drift velocity, thereby slowing down the current, increasing the resistance. Now, for a material that is obeying Ohm's law, this is its resistivity. The actual resistance is denoted with R, and that is its resistivity times its length all over its cross-sectional area. Now, the units on resistance, they are ohms, which is denoted with the symbol omega. Omega, ohms. And so if you look, as you up the cross-sectional area of your wire, you decrease the amount of resistance. Think about a fiber optics cable or a phone cable or something like that. A phone line doesn't really need to be very thick because it's not transferring a lot of information. But a cable transferring high-speed data needs a thicker or a larger cross-sectional area because it's transferring a lot more information. Now, another very important equation when we're talking about resistance. Potential is equal to IR, V equals IR. And for a material that is abiding by Ohm's law, if I were to graph voltage and current, I would get a line like so, with the slope being equal to resistance. So, that is a brief tutorial on resistivity and resistance.